this. Collections. So we're now back again. So you want to write this again. Collections of open intervals. That is intervals of the form A comma B. All right. So, for instance, let's say 3 to 7. This is a set, Jake. This is a set, and let's call it O for open, and let's give it an index number 1. Okay. This is another set. Let's say O of 2. The open interval O, or the set O with index 2, and let's say this one is from 7 to 19. Okay, so, and let's say the indexes go all the way to, they are, let's say 5 index numbers are being used. So there are more sets here. Let's say this one is 100 to 101. This is a set of real numbers. You rewrite this. Set. So this is a set. This is a set of real numbers. Real numbers between 3 and 7, not including 3 and 7. Yes, do you understand?
Yeah.
So we can, yeah, right? We've done this before. So this is 3 and 7. It's all these guys in here. But 3 and 7 are excluded. So all the real numbers, how many are there? Infinitely many. So this is an infinite set. And what we have here is a set O, an open interval over here, O sub 2, O of sub 5. So the index numbers are coming, are each, okay, let's see. So the index numbers are stored in a set called A. Okay, I should write this. Let's see, I'm going to write it here. So I'm going to delete all of this. You understand that business, right?
Yeah.
Yeah, you know the other form is the closed interval. This is also a set. This is a closed interval. And this set has all the numbers between 3 and 7, including 3 and 7, right? Okay, so now I think this is going really well, thank God. All right, so I think this is where I'm going to start next time too. So now A, 2, and 5 are in this set here. And let me use the colors here. 1, 2, all the way to 5. These are coming from the set A. So the index numbers 1, 2, and 5 are coming from the set A, defined as all alpha belong to How do we do that? Yeah. Oh. So alpha. Okay, yeah. A is a set that contains alphas. A is a set that contains alphas such that alpha is less than or equal to 5 or greater than or equal to 1. Okay, so index numbers for our O's are coming from this set called A. Okay, and then now how's another way to write this? This would be, we could also write this as 1, 2, 3, 4, 5, right?
Yeah.
And we refer any one of these as a alpha. Okay, now what I'm going to do is I'm going to collect all of these sets into a set called O. So here is our set O, and I'm going to take these open intervals and throw them in here. So O1, O2, O3, O5, O5, and we are done. So O is called indexed family of sets or a collection of open intervals, and it's indexed. So that's one way to say that, or another way to write this. This is called when you list all the elements, right?
Yeah.
If you don't want to list them, then you write it like this. You go, O is a set that contains all the open intervals, all these sets whose index number is alpha, such that alpha, why am I having trouble with alpha? Alpha belongs to the set, the indexing set A. So this guy is O without anything is the index family of sets. This is an open interval, and this is the index, and this is the indexing set. I think I killed this thing. Yes.
Yeah.
It is very confusing, by the way.
No, I mean, I'm kind of, I mean, you're doing a pretty good job because I'm following. So
yeah, I know. I'm fucking impressed
I haven't
by
been
myself.
like, what?
Yeah. So in the end, this is the key here. This O is the index family of sets, and it contains all these open intervals, each one indexed by the alpha, and alpha belongs to A, which is set of natural numbers, right?
Yeah.
So now we go to, oh yeah. And why do they always have to complicate things? But anyways, now let's look at a definition and 1.4. I don't know. Okay, all right. Let's do one definition and then we are done for today. Okay. So we got this down. So I think I can go straight to this, and this is pretty clear, right?
Yeah.
Yeah. So okay. So now we can write the definition that we needed to. All right. So here we have let S. We are doing, okay, we're doing two definitions. And this is also from Belding and Mitchell. We are trying to do definitions. First thing we wanna understand what an open cover is. This is the first thing we want to know. And the second thing is called finite subcover. These are the two things that we are going to define today. Okay, so the first line of the definition goes let S be a set of real numbers. Okay, so and actually let's draw a picture for this. Oh, I can just draw it right here. The real number line, and then our S be the set of real numbers. So from here all the way to here, this is our S. Let's make it bigger. Let's actually make it. Okay. Bigger than that. So we have the blue lines, and right here we have the red line in the middle. Can you see the colors?
Yeah.
Yes.
Yeah.
Are they almost kinda?
You can see it, I think.
That's the problem with this. Even though I have a 4K. Okay, I'm gonna make it bold.
Yeah, you can see that.
Okay, this is set S. So it says let S be a set of real numbers. So we put it on the number line. Then it says an open cover. This is an open cover for S is a collection of, yes, open intervals. And what are open intervals? They are sets of real numbers, right?
Yeah.
So an open cover is a collection of open intervals, and it gives us the set itself. So we're going to have, this is O here, alpha is the index, such that alpha belongs to the indexing set A. So in other words, this thing is actually going to look like O1, O2, O infinity. If A had all the natural numbers in it, right? So something like that, such that then it goes on to say, so I'm going to delete, I could just write below it, such that each point in S each point in S is contained in at least one open interval. Okay, so right now all we have, the illustration is just for this line here, right? Now we have to add that. So before I illustrate this line here, let me do this here. We have a guy here. This guy is standing here. Do you see the guy?
Oh, yeah.
Yeah, okay, why don't you finish writing and then I'll...
I got it. Yeah, I see the guy.
You got it? Okay. We've got another guy here. And another guy, let's say here. And it is raining. Rain. It is raining hard. How many umbrellas do we need to cover these guys?
3. Right.
Actually, I'm going to use a giant umbrella.
Oh.
And I'm going to stick it into the ground here. And I have covered all 3 guys who are standing on a real number line. So we have been able to cover these guys with just one umbrella. Sometimes I call an umbrella an open interval, even though it makes sure they don't get wet. Another way to do this is I could use 2 umbrellas, right?
Yeah.
One, that's where you were going when I stopped you, didn't I?
Yeah.
So 2 umbrellas, stick it here, and another one here. But a little doggy shows up right here. This is the dog. And this is such that each point in S, this is our little S, is contained in at least one of the open interval. Is the doggy has an interval over it?
No.
No. But right now everything is working. We got 3 guys, they're all covered. We have let's say just a small person shows up. And so we need another interval, another umbrella. Now every person, little or small, have a cover on them, right?
Yeah.
Now let's go on to our set here. So this is our S, and the S is cut up into intervals. Make this slightly even bigger. So we have the set S, and let's cut it up into intervals, right? Why not, right? So we have an interval here. We have another interval here. And let's say our third interval is this guy here. Let's make this. We'll make this interval. And okay, we could throw in okay, we got 3 intervals on the set. So what we have done is this number, the number sitting right here. Okay, now what happens is, oh, okay, I'm sorry. This is wrong. I'm gonna have to watch this video. This is the wrong way to look at it. Okay, but this is the correct way to look at it. So how many points are there on R?
There's an infinite.
I mean, sorry, the S,
Oh.
which is the subset of R.
It is
Real numbers, which means
yeah, there's a finite.
infinite.
It's infinite. Yeah, okay.
1, 2, 3, it's like forever. Okay, so let's start covering it up. We want to make sure that every point in this set is such that each point in S is contained in at least one open interval. So let's put our interval right here. This is our first interval. And it will look like this. So O sub 1, we pick this up. Let's say this interval is 1, 2, right? So I could put this equals 1, 3. So this is 1 and this is 3. Now, is the last line satisfied such that each point in S is contained in at least one open interval? Have we achieved that yet?
No, we have not.
How many points have we enclosed in an open interval currently? All the points between
1 and 3.
And not including 1 and 3, right?
Yeah, between 1 and 3.
So all the things in red here are now contained in one of the open intervals from the open cover. This is the open cover. And we took one of these O alphas and covered some points in S. So let's continue. So this is S. I'm just going to bring it down here. I want to go fix, maybe we should cover this, right? There are some empty here, right? So, okay. So I'm going to stick an open interval from the open cover right here. Let's say I do this. This is our O2 equals, what interval should I put here? What numbers?
Probably would be like 0 to 2.
Very nice. 0 to 2. 0 is sitting out here, but the numbers starting at half right there, all the way to 1, but not in, and now including 1. So now is 1 in an interval, open interval?
Yeah. Oh, yeah, it is.
Now it is, right? So all the elements from here, whatever here is, all the way to the 3, but not including 3, are now covered by 2 open intervals, O sub 1 and O sub 2. O sub 1 is 1 and 3, and O sub of 2 is O and 2. All right, so next is, maybe we could do something here. Let's cover, let's try to cover. All right, I want to actually, sorry. So I'm going to stick O3 here. Let's come up with some numbers. Let's say 5 and 6.
Yeah.
What? Why not, right? So we have 5 here and 6 here. And now, how many points are contained in open intervals from the open cover, which is this set here? All the points from here, not including 3, and then from 5 to 6, not including 5 and 6. So 5 is a point that is still not covered by an open interval. 3 is a point that's still not covered by an open interval. 6 is. So I think we need to throw in some more stuff, right?
Yeah.
So let's finish up. Let's put a giant one here. This one is going to be, let's call it O4. And O4 is going to be, I'm going to do a dotted line or dash lines. Okay, dash lines. What numbers should we go for? This could be 5.5.
Yeah.
All the way to, let's say, 13.7. Yeah?
Yeah.
And so now, so which points are still not covered? Between?
3 and 5.
Plus the points between 3 and 5, right?
Yeah.
So 3 is not covered, 5 is not covered, and all the infinitely many points between 3 and 5, right? So we need one more cover. So we've got 1, 2, 3, 4, and we're almost done. So let's cover, we could do it right here. Getting a little messy, or I could do it on the top. Let's do it on the top here. We'll move this to O1. This was O1, and that was 1, 3. And now we're going to put this guy here. And the notation for the interval is these, right?
Yeah.
On the number line. So this is going to be right here. So dashes again. And actually, we don't need to go all the way here. We could go all the way to right here. And this would be our O5 equals, let's call this 2, and let's call this 5.4. So 2, 5.4. And now everything is covered. Do we agree?
Yeah.
And the fact is that this is a finite cover. So it's kind of like, but we'll do that next time. So this is a good, I think, good way to think about it.
Yeah, I like the range. That's
yeah, that's super original. The first time in a math class we have had rain. And also the intervals are these guys. This and this, this and this. And this is not notation, this is just for us. And these look like the umbrellas, right?
Yeah.
Okay. And just to remind us, this thing here is the S. And so there are a bunch of proofs that depend on working with this kind of stuff. So that's what the next class is going to be about. Oh, yeah. All right. I'm kind of happy about today's. Let's do this. Stop.